Kia ora and welcome to this video, question 3 of the 2023 Scholl Calc exam. This question is all based on differentiation. In the first part we have a parametric curve of which we need to find the stationary points on it. The second part, part B, is a very typical related rates problem. We're going to look at this in a couple of different ways. And then part C is quite tricky to get your head round, but it is a pretty reasonable optimization problem once you work out the equation that you need to differentiate. Okay, so part A, this is fairly typical of an NCEA problem, probably at merit level, but the justification is a little bit trickier. We've got to determine the nature of the stationary point. So first up, to find the stationary point, we need to find a dy dx. So we've got x is equal to 2t minus 3t cubed, in which we can find dx dt. Derivative of that with respect to t is 2 minus 9t squared. Our y expression is t e to the t. To differentiate this, we need the product rule. dy dt is equal to the derivative of t multiplied by e to the t. So it's 1 times e to the t. And then the derivative of e to the t times t, which is just t e to the t. And we can factor that as t plus 1, all multiplied by e to the t. So dy dx, which is our gradient function for this parametric curve, is the dy dt, t plus 1 e to the t, all over the dx dt. And we want to make that equal to 0. Making it equal to 0, sure, we need to consider that the denominator is not allowed to be 0. That is two different t values where that can't happen, but they're not stationary points. The stationary points of a curve are where the gradient is 0. So we're solving t plus 1 e to the t equals to 0 because it's already factored. We just need to consider the factors. E to the t never equals 0, so t must equal minus 1. There's only one stationary point on this curve. The question asks us to find the coordinates of that stationary point, so we do need to use the original equations to find the x and y values. Okay, so t equals minus 1. When we substitute that up into the first equation, 2 times negative 1 minus 3 lots of negative 1 cubed, that comes out to be a value of x equals 1. And then similarly for the y value, we get negative e to the minus 1, or negative 1 over e. Up to you, but those are the exact values. We could approximate them in decimals if we wanted to. Now, determining the nature of the turning point. There are two different ways that you can do this. The first, which is a little bit tedious, but it's to find the second derivative. So if we want to differentiate this parametric curve one more time, well, we take the first derivative, which we've already worked out, and we differentiate that again. But the important thing to realize is that we're differentiating with respect to x here. And this expression, our current first derivative, is a function of t. So we actually need to do this implicitly. And we differentiate the first derivative again, but with respect to t. And then we multiply by dt dx, which, as the t's cancel, we're actually differentiating with respect to x. It's implicit differentiation, but if you'd never seen that before, it's on the formula sheet. It says that you need to differentiate with respect to t, the dy dx, and then times by dt dx. A real common mistake that students make is they forget this factor here. And in this particular problem, if you forget that factor, your stationary point changes from a min to a max. Okay, so differentiating that first thing, we need the quotient rule for that. Okay, if you want to follow along by going and making this whole top thing here f and this bottom thing g, then the quotient rule tells us f dash g, so we need to differentiate t plus 1 e to the t. That's the product rule in there. T plus 1 e to the t differentiates to t plus 2 e to the t. I'll let you fill in the details there, but I've used product rule, just like I did to find the first derivative. and then that's multiplied by the denominator. Then the next part of the quotient rule says minus g dash f. So be careful here, we're minusing negative 18t, which is the derivative of the denominator, times t plus 1 e to the t. And then all of that is divided by the denominator squared. And then we've got a times by dt dx, which is the reciprocal of dx dt. So we get another 2 minus 9t squared. We actually need to write this as 2 minus 9t squared all cubed because of that extra factor of dt dx. Okay, now we sub in t is equal to minus 1 because that's how the second derivative test works. You substitute the point in that you're wanting to test. Now this is a nice value because a whole heap of the stuff disappears. This whole factor here is going to cancel when you make t is equal to minus 1. And so we get 1 times e to the negative 1 times by 2 minus 9, all divided by 2 minus 9 cubed. Okay, so that first part, 1 times e to the negative 1, is positive. The second bracket in the numerator is negative, and then the denominator is a negative thing cubed, so that's going to be greater than 0. And when it's greater than 0, the second derivative tells us about concavity. So a positive concavity means that the curve is concave up, which means it's a minimum. Therefore, minimum, or local minimum. Now, you could just use the first derivative test for this particular question, because the second derivative is a little bit tedious. So on a side note, or use the first derivative test, but you've got to be really careful how you apply it with a parametric curve, because what we want to do is test time. Oh, it's not necessarily time, but usually I think of t as time. We want to test t values either side of our stationary point. So we know that negative 1 is our stationary point, and actually I'm going to need a bigger table. And let's say I test a t value minus 0.9 and minus 0.1. And you might be thinking, hey, hold on a second, minus 0.9 is greater than minus 1. Why am I writing it on the left? And why am I writing minus 1.1 on the right? And it turns out that on the graph itself, t equals minus 0.9 is to the left. When you find these x values, okay, and I'm using the x equals equation to do this. When I find the x values for these corresponding t values, I get 0.387 for this one, I get 1 for this one, which we already found, and I get 1.793. So moving from left to right on the picture, remember that our coordinate system is an x-axis, y-axis situation. When I move from left to right, I'm actually decreasing in t values. If I move from right to left on the graph, which goes like this sort of thing, and I'm moving from right to left, I'm actually increasing in the t values. Okay, so why is that important? Well, when we find the gradient at these points, the gradient at t equals minus 1 is 0. We knew that. It's a stationary point. You can verify these numbers, but I'm getting them from the first derivative. That one's a negative, and that one there's a positive. And it looks like, oh, maybe we've got a minimum. Well, we know we've got a minimum because we've already tested the second derivative, but it goes slope down, slope 0, slope positive. But if you had your t values run the wrong way, then you would have come to the conclusion of it being a maximum, because you would have gone positive slope 0, then negative slope. Okay, so it is a minimum, but you've just got to make sure when you do the first derivative test with a parametric curve that you have your x values going from smallest to biggest. It doesn't matter about your t values going from smallest to biggest. Hopefully that made sense. Okay, second question about a baseball diamond. We've got a couple of ways that we can solve this problem as well. The first one is, or the way I did it, is to write this distance that we're trying to find, this distance here, the player's distance from third base, to write it as a function of time. So I did that straight away. I said, okay, Pythagoras tells us what that distance is. It's d is equal to the square root of 27.4 squared plus, let's call this little bit here, x squared. And then how does x depend on time? Well, if we say that time equals 0 is where the player is currently, even though they left first base, let's just go with t equals 0 where the player is at the moment, then they start off at 17.4 meters away from second base. So x is initially 17.4, and then it decreases by 5 meters per second because we're told the player is running at a rate of 5 meters per second. So we can switch the x variable out and just write it directly as a function of time by putting 17.4 minus 5t in there, all squared. And what I've done by making this function an explicit function of time is meaning I just differentiate it. I just find out that speed. I don't have to do any related rate stuff because I've just done the related rates bit. I've made my expression only have one independent variable. Okay, so that's where I'm going to start that's the way I did the problem. So we go distance. Actually, I'm going to, rather than use d for distance, I'll use s, just to not confuse with the differential notation. It's the square root of 27.4 squared plus 17.4 minus 5t all squared. Now, your expression in here could have been different depending on when you set t to be 0. So that's not a big deal. You just need to know what to sub in at the end. And I'm going to sub in t is equal to 0 to answer the problem. Okay, so differentiating this, ds dt, it's something to the power of a half. So we've got a half. The stuff underneath the square root gets rewritten. Oopsies, not 17.4. 17.4 minus 5t all squared to the power of negative 1/2. And then we need to multiply by the derivative of the stuff underneath the square root, which is 2 lots of 17.4 minus 5t, all times minus 5. Okay, now we can tidy a little bit of that up because we've got a 2 there that cancels with that 2. We've got a negative third, so we can write minus 5 lots of 17.4 minus 5t on the top, and then the square root on the bottom, 27.4 squared plus 17.4 minus 5t all squared. So that's our derivative, and now we're subbing in t is equal to 0. When the player, how am I going to word this? When the player is 10 meters from first base. The player is 10 meters from first base, ds dt equals, we're subbing in t is equal to 0, so we've got minus 5 times 17.4 all over the square root of 27.4 squared plus 17.4 squared. Okay, and that comes out to be minus 2.68 meters per second at that point in time. So that's one way of solving the problem. Another way is to use related rates, as I mentioned kind of from the outset. So if you have that triangle, which looks kind of like that, and that was 27.4, and this dude here was x, and if we don't write x as a function of time, that's okay, we don't need to. We can call this s. We've got Pythagoras telling us that x squared plus 27.4 squared is equal to s squared. And you've got two ways of actually doing the related rates. You can either go ds dt is equal to ds dx times dx dt. We know that dx dt is minus 5, and ds dx can be worked out using a similar method as before, and I rearranged the equation. So I make s the subject, s is the square root of x squared plus 27.4 squared, and ds dx is x over the square root of x squared plus 27.4 squared. So we just need to times that by minus 5. And that'll give us the same result. Or we take our equation, which is the equation that connects these variables together, and we differentiate it implicitly with respect to time, because we know that x and s both depend on time. We just don't get to see the t's in the equation. So if I differentiate this whole equation with respect to t, that first term will be 2x times dx dt. The second term will disappear because it's a constant. And the right-hand term on the right-hand side of the equation will be 2s ds dt. And remember that we want ds dt, so we can divide those 2's out. And we can go ds dt is equal to x divided by s times dx dt. And you might have noticed that that's actually the same setup that we had in both of the other solutions, because this dude in the denominator here is actually s. And we needed to then times all of that by dx dt. In the top equation, in our first method, that there's s at that particular point in time, that there is x, and then we've times by minus 5. So it has the same structure for each of the solutions. And I think that last method, implicit differentiation, is definitely the quickest way to solve the problem. Okay, the second part of this question, part II, asks about how the angles are changing. So we go back to the triangle that we have. Theta 1, right angle, doesn't look like it, but it's going to do. No, it's not. Get up. This is 27.4, a constant. This is x again, it's moving. And this time we're talking about when this person slides into the base. Okay, it says slides into second base. So when x, that distance x in my diagram, approaches 0. It's a limiting kind of question. So yes, we've got this distance as s, but we actually don't care about it this time round because we're introducing theta 1. So we know that tan of theta 1 is equal to opposite over adjacent, which is easier written as x equals 27.4 tan theta, because we want to differentiate this thing. We actually want to find what d theta dt is, but a good way of starting would be to find dx d theta 1. So if I differentiate this, I get 27.4 sec squared theta 1. And then using my related rates knowledge, I'm going d theta 1 dt, that's the rate I want to find, is d theta 1 over dx multiplied by dx dt. The reciprocal of the derivative we've found. So if I take the reciprocal, I've got this, and then I'm multiplying by the minus 5 again. Dx dt is the speed that the person was running, assuming that it's the same when he slides as to the speed when he runs. Now, the limit as theta 1 tends to 0, because that's what's happening when x goes to 0. Of this expression, well, we're dividing by sec squared. When you divide by sec, it's the same as timesing by cosine. And when we make cosine, or you consider the limit of cosine, well, cosine of 0 is 1. So this limits to minus 5 over 27.4. And if you work that out as a decimal, it's 0.182 radians per second. Negative because it's decreasing. Now, we could follow a similar process for the second angle, for theta 2. But what you need to know from this question is that theta 1 plus theta 2 is equal to 90 degrees, a constant. So if theta 1 is increasing, my apologies, theta 1 is decreasing by 0.182 radians per second, d theta 2 over dt is going to be equal to plus 0.182 radians per second to preserve the shape of the triangle. One of the angles is fixed. If the other one goes up by a little bit, the other one needs to go down by at the same rate. There is an alternative way of solving this problem, but it requires a little bit of knowledge outside of the NCEA curriculum. But if you started off with the expression, the tan inverse expression, a similar function as I had before for part I, the distance in the opposite distance, x, is 17.4 minus 5t, and we're dividing it by 27.4. We can differentiate directly if we know how to differentiate the inverse tan function. And I've covered this in other videos that I've done, but if you've never seen it before, the derivative of the inverse tan function, arctan, is 1 over x squared plus 1. Okay, you can look up, there's heaps of proofs of that on the internet. So for this one, it's a little bit different because this is our x. Not x as the distance on the triangle, but x in terms of the tan inverse of x. So we need to use the chain rule to differentiate this. We've got 1 over, all of that stuff in green gets squared, plus 1, but then we also need to multiply by the green stuff differentiated, which is minus 5 over 27.4. Now, what happens when t is equal to, not 0 in this case, but we're wanting to consider what happens when that x side, when this side here becomes 0, and I'm calling this 17.4 minus 5t. So it's going to equal 0 when t is equal to 3.48. That's the value of t that I need to consider in its limit now. So the limit as t goes to 3.48 of d theta 1 over dt, well, this whole dude here will go to 0, and then we've just got minus 5 over 27.4. The same answer as we had before. Cool. Okay, part 3 of this question is quite tricky because there's a lot to sort of get your head around. And if I'm honest, I didn't solve this in a general way to begin with. I solved it by kind of using a bit of NCA level 1 knowledge and making a table to try and get my head around the situation. So to explain what I did, I made a little table. Actually, it was a slightly bigger table than that. And the first thing I considered was time between orders. Another way of thinking about that is the length of the production cycle. Length of cycle. So if they order steel every single day, then they would need to order the amount of steel ordered would be 5, because it says in the question they need to produce 5 gates per day, and a unit of steel is the amount needed to produce 1 gate. So they would need to order 5 units of steel if they were ordering steel every single day. Now, storage costs. They have to store the steel that they don't use. Well, there would be none. There'd be no storage costs if they were getting it delivered every day. They wouldn't have any left over overnight. I just kind of thought storage was an overnight fee. It's not quite clear in the question when the storage fees get applied. And then, lastly, delivery cost. You're told in the question that delivery cost is fixed. So it's paying for the order to be completed, for the truck to come out with the steel in it. It doesn't matter how much steel you've got, it's the same amount. So we're going with $5,000 here. So obviously not very optimal to do this $5,000 thing every single day just to get enough steel to make 5 gates. And then lastly, it's the per day cost, because that's the thing in the question they asked us to optimize. How much should they order each time? How often should they order it to minimize the average daily cost of delivery and storage? Okay, so we take the $5,000, we're ordering every day, so that's $5,000 per day. Then what happens if they order every second day? Well, they're going to order 10 lots of steel. This is where it gets a bit complicated. Storage costs. If the manufacturer orders a large quantity of steel every time, this will reduce delivery costs per unit, but it's going to increase storage costs, and it costs $10 per day to store 1 unit of steel. So if they order 10 in an order, 5 of it will get used to make gates. The other 5 will get stored overnight to be used the next day. So the storage costs are going to be $10 times 5, given that only 5 of the units will be stored. The delivery cost is still $5,000, and if we add on the $5,000 to the $50 of storage costs and divide it by 2, because it's 2 days, we get $2,525 per day. And I did this for a couple more just to get my head around the generalization. 3 days, 15 steel would be ordered. 5 of that would be used straight away. 5 of it would be stored for 1 day at $10, and 5 of it would be stored for 2 days, so $20. And I add on the $5,000 to the $150 storage cost, and per day 17. One last one, 4 days. If you order for 4 days, $20 steel ordered, 5 gets used straight away, 5 will charge for 1 night storage, 5 will be charged for 2 nights storage, and 5 will be charged for 3 nights storage. $5,000. If you add those two together, divide by 4, you end up with $1,325 per day. Now that's going down, but there's a point where it starts to increase again, and that's when you're paying too much storage. You're ordering steel far too far in advance, and you're not using it quick enough. So there's a couple of ways of thinking about the storage cost thing. The first is just to look at the numbers and try to find a pattern in the numbers. 0, 50, 150, and then this next one's 10 times 5 plus 20 times 5 plus 30 times 5. That comes out to be 300. And you can say it goes up 50, up 100, 150, and so on. And it's a quadratic pattern. Plus 50, plus 100, plus 150, and so on. So we could express the storage costs as a quadratic function. The second difference of the quadratic pattern is 50. So you've got storage costs is equal to 25n squared. 25n squared, does that work? No. Minus 25n. I think that's the expression that I had. I'll explain that in a sec. Yep, that works. You just check it for like n equals 4. If you go 25 times 4 squared minus 25 times 4, you get 300. So that's our storage cost, and we add on the delivery. If you can't remember how to solve quadratic patterns, the general term is you write an squared plus bn plus c. A is always half the second difference. So for us, the second difference in the pattern, it's going up. It's going up in 50s. So 25 would be our A. Bn is the linear term, and C is the term when n is equal to 0. So I can extend the pattern back and go n is equal to 0. No steel's ordered, so there's no storage costs. So C is 0. And then finding B is just using substituting a coordinate in to make it work, and I found out that it was minus 25. Okay, so that's one way of doing it. Anyway, let's go and actually write up the answer to this problem. Okay, first thing is we have the cost per day is $5,000 plus this $10 times 5 units of steel times 1 plus 2 plus all the way up to n minus 1. Okay, on the that's the general expression for what we were doing there. We just look back at our table. It was always had a 10, it always had a 5, and then the first one's 10 times 5 times 1, the next is 10 times 5 times 1 plus 10 times 5 times 2, and the last one's 10 times 5 times 1, 10 times 5 times 2, and 10 times 5 times 3, which is 1 less than the number of days in the order, which is 4. So that's where I've got this general expression from. And then the question is, well, how do I sum up these numbers? Summing up natural numbers is actually quite easy. Let's just look at a specific example. If I was to add up the numbers all the way up to 10, I can pair them up. So I can go 1 plus 10 is 11, and all of the pairs add up to the same amount, is 5 pairs. So the answer to that is 55. Now we're summing up natural numbers up to n minus 1. So I take the first and last terms and add them together. Well, 1 and n minus 1 is sums up to equal n, and then I times by half the numbers, because if there is 10 numbers, there's 5 pairs, and it actually turns out this formula works for odd and even numbers as well. So I take the number of numbers, which is n minus 1, and divide by 2. So I've got, and that's all going to be divided by n, the number of days for cost per day. 5,000 plus 50 times n, the sum of the yellow numbers, the first and the last terms added together, times the number of numbers divided by 2, all divided by n. Okay, and then that simplifies to 5,000 over n, and then this last term, the 50 and the 50 there and the divide by 2 makes 25. The n there and the n there can cancel, and we're left with 25 times n minus 1, or 25n minus 25. Now remember, before my expression was 25n squared minus 25n, but this is being divided by n, so we get the same thing. If you didn't know how to sum up numbers from 1 to n, then you could have done it as a quadratic pattern. Okay, and now we need to diff this. We want to find the optimal cost per day, or let's just call cost per day C. So dc dn, 5,000 over n is the same as 5,000 n to the minus 1, so that's going to go minus 5,000 over n squared and plus 25. That makes it equal 0 for a stationary point, in this case a minimum. And then n squared is equal to 5,000 divided by 25, comes out to be 200, and it's a strange answer, but the square root of 200 is the number of days that should be between orders, 14.14. I guess it is possible to order in a fractional day, but realistically it's going to be a whole number in the real world. So we test. You can test the cost for 14 and the cost for 15. You'll find out that it's best with 14. So, cost per day minimized if orders are made every 14 days, which is 2 weeks. It's actually quite a practical answer, actually. Order every Monday, or order every Tuesday, every second Tuesday. And how much steel should be ordered each time? Well, if they're going to make 5 gates per day for 14 days, then they need to order 70 units each time. Cool. So quite a tricky question to get your head around, particularly forming the expression, but I do recommend doing something like this, where you break it down into whole numbers and consider that before you generalize. Catch you in the last video.